So I wanted to just go over the idea of circular orbits for gravity, and then also show you an interesting result about the energy of an object that's in a circular orbit. It turns out that circular orbits aren't going to be as common. Normally, in nature, we're going to see something that's more elliptical, like the planets travel in elliptical orbits. They don't travel in circular orbits. But in any case, it allows us to use some of our previous physics knowledge and actually see something that is sort of physics-wise pretty important, and we can derive it relatively easily. So let's imagine that we have a satellite orbiting the Earth in a circular orbit. I've determined that the orbit has a radius of r. It's maybe not labeled so great, but I didn't want everything to overlap. Maybe it doesn't look circular, but use your imagination and pretend that it's a pretty circle. So the Earth is at the center, the satellite is orbiting. Now, if I wanted to think about this from the point of view of Newton's second law, where the sum of the forces equals the mass times the acceleration, I would say that because the satellite is going in a circular path, that my acceleration is going to be centripetal. So I'm going to write the acceleration as v squared over r. Then we want to think about, well, what is the force acting on the satellite which keeps it in its orbit? And of course, that's the force of gravity. The force of gravity that exists between the Earth and the satellite. And it is attractive, and that's why I drew the force of gravity in that direction. So the force of gravity between the two is big G times the mass of the satellite times the mass of the Earth divided by the radius of the path squared, and that's equal to the mass of the satellite times v squared over r. Now, we notice that the mass of the satellite is on both sides, and we can get rid of it, except that I didn't want to do that. So I'm going to undo that and make a mass here. So I have the mass of the satellite and the mass of the satellite, because what I want to do is I want to use this expression to write the mass of the satellite times v squared would be equal to big G times the mass of satellite, the mass of Earth, over r, if I rearrange this. And you might ask, why are you doing that? Sorry about the mass, but the reason that I'm doing this is because this term almost appears in the energy term. So now we're going to sort of switch from what we found here and focus on the energy of the satellite while it's in its circular orbit. Its energy consists of two different types. It's obviously going to be moving because it's orbiting, and it also has a gravitational potential energy. So I've rewritten the kinetic energy and the gravitational potential energy right here. Now you might see why I was interested in this expression, because I could substitute in for the mass of the satellite times v squared. I could substitute in this expression. So I'm going to rewrite that. I have 1/2, and then I'm going to write big G, the mass of the satellite, the mass of the Earth over r, and then minus big G, mass of the satellite, the mass of the Earth over r. So you might see that what I have is two terms that look a lot alike. And I can relatively easily add those together. I'm going to factor something out just so it's more obvious. If I factor out this common term, I have 1/2 minus 1. And so I end up with minus big G, mass of the Earth, mass of the satellite, over 2r. All right, so now that I've moved, you have a chance to see that. So using the idea of Newton's second law and the fact that moving in a circle made it centripetal acceleration, and using the fact that gravity was the force that kept it in that orbit, I was able to come up with a way to express basically the kinetic energy, but in terms of gravitational terms. And that allowed me to combine the kinetic energy and the potential energy together into a single expression, which represents the total energy of the satellite when it's in that orbit. And again, another interesting thing that came up is the total energy is negative, which I think can be instinctively disturbing. You're like, it doesn't seem right that the total energy would be negative, but it's okay, because in physics, the fact that it is negative means something. It means that these two objects, the Earth and the satellite, are bound together in a system. This is a bound orbit. And as long as the satellite stays where it is, going the speed that it's going, it's not going to leave. And I always like to compare this to the very simple model of an electron in an atom. And if you learned about that in chemistry, you learned about the energy levels that that electron had. Remember that all those energy levels were negative until it reached zero. And at zero is the point where the electron can leave the nucleus and leave the atom, and the atom becomes ionized. This is really a similar idea here, is that while these two objects are bound gravitationally, the total energy of that system will be negative. As this satellite moves further and further away from the Earth, its total energy will become less and less negative. It'll be starting to approach zero. And at the point where that satellite has an energy that is zero is the moment where it can escape from the gravitational pull of the Earth and escape. And so that negative sign means something, and I wanted to show you how we come up with that expression. And that's it for our video on circular